This video is going to cover stress-strain relationships and how to use the equations that we covered in the stress-strain diagrams lecture. So we actually only had 3 equations, really technically 4 if you want to consider that modulus of rigidity had 2. But we start off with modulus of elasticity, that's E, is equal to stress over strain. This is normal stress over normal strain. For the modulus of elasticity, if we're talking shear, that's G, that's the modulus of rigidity, and that's shear stress over shear strain. So those really aren't that bad. We had one other equation. We had Poisson's ratio, and that's nu, and that's equal to minus the lateral strain over the longitudinal strain. Now, just to make sure that everything's pretty clear on what is latitudinal and what is longitudinal, longitudinal strain is the strain down the axis of the member, which is effectively your normal strain. So if you want to know how much a rubber band shrinks in cross-sectional size when you pull it and stretch it out, that's what Poisson's ratio is going to give you. And technically there's one other little equation here for modulus of rigidity, and that connects our modulus of elasticity to, and Poisson's ratio, to the modulus of rigidity. So it's E over 2 times 1 plus nu. So there's technically our 4 equations, 3 if you just consider that modulus of rigidity just has 2 different ones. And it kind of depends on which one are you supposed to use. Are you supposed to use that simple equation, or do you use this equation? And that question comes down to what information do you know? Is your system in shear? If your system is in shear, well, then you're going to be using shear stress and shear strain. If your system is not in shear, then you're going to be using things with normal stress, normal strain, and Poisson's ratio to figure out the modulus of rigidity for the material. So it kind of just depends on the problem, and these type of problems are really, really simple. They'll give you pretty much every bit of information minus one piece, whatever that one piece might be, and you just have to plug it in and see where the math kind of takes you. Again, just make sure that you're watching your units. So let's go ahead and do an example. And in this example, we're going to not have everything given to us straight up. So we'll have a stress and strain curve here, and we're going to zoom in pretty close. Let's say that we're going to zoom in really close on this guy. So he has a straight line, and then he does a little bump and then a little dip. How often do they look like this? Actually, quite frequently. If you realistically do a test on, say, something like steel, it's going to be a straight line for sure, but that little peaky area over here is sometimes not very well defined. So you just kind of stay out of that range. Sometimes it goes up and it dips down, sometimes it doesn't, sometimes it just kind of goes off at an angle. All little materials are different because that's just the behavior of materials. So information that they do give us for our stress strain curve, we're going to have that here is about 34 KSI for our stress, and at that same spot, let's say that they gave us a strain, and this value is 0.001. And remember that strain is in inches per inch. Actually, kind of unitless in a way. You could talk about it in terms of a percentage, because, I mean, technically it doesn't really have units, but it's always good to keep writing your units just to make sure that you know what it is that you're getting for an answer. So we have a stress strain curve, and this material, let's draw a pretty little picture of it. We've got this little bit of steel here that we're going to pull. Oh, that's quite a terrible drawing, actually. Let's say that's a bit better anyway. So let's say we have this steel piece here, and we're going to be pulling it. So we have an applied load P. All right, so it's in tension. We're pulling it each direction with the applied load P. And the total length of this bar, say the total length from here to here is, let's say it's 1 foot, but that's kind of weird to talk about feet, so we're going to say it's 12 inches. And let's say in the horizontal direction here, kind of sort of, this direction, let's say that that is 2 inches wide, and then vertically, let's say that this little bar here is 0.25 inches tall. So it's not very big, right? It's kind of skinny, have a little cross section, and it's kind of long, across 12 inches. What we do know about this material, let's say that they gave us that Poisson's ratio is 0.29. And what we want to do, we want to find the following things. So we want to find, number one, the value of P that we have here on our little strap, the value of P if the strain is 0.0006 inches per inch. And that's just not enough stuff to find. So number two, what we're going to find is why not also calculate modulus of rigidity. And number three, we're going to calculate more stuff. We're going to calculate the deformation of the strap in the longitudinal direction. And we want to know the deformation of the strap in the latitudinal directions, plural. There's 2 of those. At the time that strain in the longitudinal direction is 0.0006 inches per inch. So that's what we're going to try and find, all these things. It's kind of an awkward start compared to most. You're not just given, numbers and say, hey, go plug and chug. Instead, you kind of have to find your numbers. If you want to find P, you need to know your stress. You're given a strain. And how would you find P? I mean, if this was a very detailed graph, you could obviously go over here and go, yeah, there's about 0.6 come up. Yeah, it's about this value, and kind of read it off the chart. But in this case, since we don't actually have any numbers whatsoever, that's probably not the best idea. So instead, it might seem like, oh, I don't have enough information, but I do, right? This line is a constant slope, and that constant slope is modulus of elasticity. So whereas they didn't ask us to solve for modulus of elasticity, it's probably a good thing to solve for. So the modulus of elasticity is simply the slope of the line, and the slope of the line is going to be the rise, which is stress, over the run, which is strain. So good thing they gave us a point, right? They said that the stress is 34 KSI, kips per square inch, and we had at that moment a strain of 0.001 inches per inch. So our inches per inch already cancel each other out. We're going to get the modulus of elasticity in terms of KSI, and we get 34,000 KSI. That's the modulus of elasticity. What does that do for us? Well, now if I plug in a value for strain of 0.0006, I can find what my stress is. I know my area. I can solve for P. So kind of like we go a little bit forward, we go a little bit backward type thing, but we're just playing with the numbers that we do and don't know with very, very simple equations. So E was 34,000 KSI, and that's equal to the stress that I'm not sure about because I don't know it yet, over the strain value that they gave us of 0.0006 inches per inch. So we're going to get a stress value from this guy of 20.4 KSI. Okay, that's really nice, and we know, of course, that stress is very simply just the load over the area. So we have stress. We said our stress again was 20.4 KSI. And we have our force. We don't know it. It's P. He's what we want to find. Over the area, and the area is that 2 inch by 0.25 inch. So 2 inches by 0.25 inches. So voila, all we got to do, multiply over here, and we're going to get that P, the value of P that we wanted to know when the strain is at 0.0006 inches per inch, is 10.2 kips. Yay, there's part number 1. So sometimes you're going to have to read off a chart. Not saying it's very hard to read off of a chart, right? Find one value that's really easy to read, one that, if they don't specifically give it to you in this fashion, go find a value that's lining up pretty well with one of these numbers and read across and see what number you get. Because the slope of this line is the same anywhere along this line. So pick any rise, any run that you can quite easily see, and that'll make the problem a lot easier to solve. Once you have E, just plug in any number for either stress or strain, you'll find the other one. Yep, so that's pretty simple. Next, we wanted to find G. That's the modulus of rigidity, but we're not in shear. If you look at that picture of the bar over here, it is very clearly not having any shear stuff. It's just a bar. It's being pulled. That's it. That's only normal forces. Axial normal forces. So we don't have any shear information, so we cannot use the shear stress over shear strain because we don't have that information. So instead what we do have is we do have modulus of elasticity over 2 times 1 plus Poisson's ratio. And we solved for modulus of elasticity, and here it's 34,000 KSI, and they gave us originally a Poisson's ratio of 0.29. That's fantastic. So again, we're just going to plug it on in, right? So we said that modulus of elasticity there at the top is 34,000 KSI. This is divided by 2 times 1 plus, we said 0.29 for a Poisson's ratio. So we're going to find that the modulus of rigidity is going to be, I'm going to round here a little bit to 3 significant figures, and that's 13,200 KSI. Same units as modulus of elasticity, because again, shear stress has units of pressure units, so KSI. Shear strain is in radians, so of course that's not going to matter at all. And same thing with the other part of the equation, that modulus of elasticity is in KSI and Poisson's ratio is unitless. So the top of our fraction always seems to have units and the bottom side does not. So therefore our units are the exact same as the top side. So cool, so there we go. We found 2 things already. Next up, the only other thing to find is the latitudinal and longitudinal deformations. So how much it's actually changed in size when that strain is 0.0006 inches per inch. So this is kind of easy since we already were given that strain. And this is the longitudinal strain because it's the normal strain. And we said that value is 0.0006 inches per inch, and we know that strain is simply the deformation over the original length. So deformation is what I want. What is the original length? The original length in the longitudinal direction is 12 inches. Be very careful, of course, when you're looking at your problems, because if it's obviously in feet, don't forget that you might want to convert those to inches. Technically, if you didn't convert them to inches, you would get an answer in feet. But that's usually not what you want. So we did say that instead of having L naught, we said we had 12 inches. Okay, so we're going to multiply that out, and we're going to get that our deformation in the longitudinal direction down the axis of the member is 0.0072 inches. You might be thinking that's really small. Yes. In the elastic region, you do not see the strain. If you did see the strain, you are well past the elastic region of the member. So are you going to be able to see 7 times 10 to the negative 3 inches? No, you're not expected to. So anyway, that's our longitudinal deformation. Now we need the latitudinal deformation. And how to calculate that, remember that Poisson's ratio is the negative lateral strain over the longitudinal strain. The negative doesn't necessarily connect to his buddy lateral up at the top. He's just a negative in front. So effectively what this means is when you stretch something out longwise, the cross-section kind of contracts and gets smaller, versus if you were to squish something longwise and make it shorter, your cross-section would kind of bulge outward. So either way, the negative's not necessarily attached to any one of those. He's just kind of floating in the front. And again, we said Poisson's ratio was 0.29 for this problem. And we actually don't know the latitudinal strain, but we do know that the longitudinal strain there, 0.0006 inches per inch. So multiply it out, and what we're going to get is that for our latitudinal strain, it is going to be a negative number. And why is it negative? Again, negative means it is in contraction. So as the longitudinal direction is pulling, the cross-section is, of course, shrinking, and that makes perfect sense. So Poisson's ratio is always positive, so one of these has to be shrinking, not pulling, and in this case, since we are pulling it out further, our cross-section is getting smaller. So we do have a negative number, and it's negative 0.000174 inches per inch. Now again, remember that strain is very simply, latitude or longitude doesn't actually matter, the deformation over the original length, right? The change in the cross-section, the change in length, the change in it could be diameter, right? It's the change in directional thing over the original directional thing. So we're going to do this twice, right? Because we have two, actually in this case, we have two separate directions. We have the 2-inch direction, and we also have the 0.25-inch direction. So we're going to get two separate ones. If you had a round bar, you're literally just looking at the change in like diameter compared to the original diameter, because the cross-section is like uniformly a circle. So it's not going to magically become an oval of some kind. It's just going to shrink uniformly across the member. So, but in this case, because we do have a rectangular thing, we have two separate directions, the x and the y, so we're just going to evaluate this separately. So again, we have that our latitudinal strain, we said negative 0.000174 inches per inch is equal to the deformation in the, we'll start off with the 2-inch direction here. So the deformation in the 2-inch direction over the original length, which is 2 inches, who would have guessed? We multiply that out, and we're going to get that the deformation in the 2-inch direction is equal to 0.000348 inches. Again, very tiny, not really surprising when you think about it. You shouldn't be seeing any of these strains or any of these changes visibly. And if we do it again for the other direction, we have 0.000, those are negative values, by the way, 174 inches per inch is equal to, this time, the deformation in the 0.25-inch direction over the original, which was 0.25 inches. And again, all this negative number means is that we are actually getting smaller, so our deformation in the 0.25-inch direction is going to be a negative 0.000044 inches. Yeah, I mean, you kind of would expect that if you're only looking at like a 1/4 of an inch, that you're really not going to notice much of a change, versus 2 inches. Either way, you're really not going to notice these changes. So both of these are getting smaller. Again, at this point, solids is not actually too difficult. If you understand what goes into the equations, you're literally just looking at, okay, well, I know stress, I know strain, I know what these are, and you're just plugging in a whole bunch of really tiny equations and finding the one number that you don't know. So it's just manipulation of equations at this point, sometimes pretty simple, sometimes, I guess, kind of not, but really there's not much else that they can ask you to make stress-strain relationships hard, unless it was a problem in shear, but again, you just use shear modulus of rigidity instead, and it's pretty much all the same. So hopefully that makes this topic relatively simple.